Good morning. Today we're going to start your Unit 8 packet, and we're going to be discussing gas laws in this unit. So these notes, since we are going to be drawing a few pictures, you'll notice that we are not using a PowerPoint for this unit. We're going to be taking notes on an attached fill-in-the-blank note sheet that you have in your packet. So you'll see the objectives listed at the top. We will explain the relationship between temperature, volume, moles, and pressure of a gas. We'll perform pressure conversions. We'll learn about Dalton's law of partial pressure, and then we'll use gas laws to solve problems, and we'll apply gas laws to reaction stoichiometry. Now, I'm going to actually go through most of this today. We won't get to the gas stoichiometry, but I am going to explain these first 4 bullet points. So first we need to go through and talk about the different relationships in gas laws. So before we can do that, you need to know about the kinetic molecular theory. Now, when you see the word kinetic, you should think movement or motion. Molecular, obviously that's talking about molecules. So we're talking about the movement of molecules. And specifically, we're talking about gas molecules. The kinetic molecular theory states that gases are moving randomly, chaotically, and they are bouncing off of anything they bump into, which would be their container walls. When they collide, they exert a pressure on the container. So keep in mind, as we're talking about gases, that they are constantly moving. It's random, it's chaotic. They don't lose momentum. As soon as they hit something, they bounce off of it, and then they collide into something else. And that creates pressure. Now, what is the relationship between temperature and pressure? In other words, if we increase the temperature in a balloon, so I'm going to draw 2 balloons, and we're going to assume for this that the volume is constant, meaning that these 2 balloons have the same volume, they're the same size, and nothing that we do with the temperature is going to change the size of those balloons. So in this first balloon, I want you to imagine that the temperature is low. So imagine that you have a little gas molecule in here. When gases are cold, as they are in this balloon, they don't move very fast. So this little gas molecule is just barely creeping along. It's not moving as quickly. If we were to measure its movement in like a period of 5 seconds, it's not going to be moving very far. Whereas in this balloon, we're going to say that the temperature is high. So following the movement of this one gas molecule, now it's really hot, so it's moving like crazy. So heat causes the gas molecules to move faster, more quickly. They're going to cover more ground. And if we are measuring pressure as how much force these gases are exerting on the walls of their container, we would say that there's more pressure in this balloon than there is in this balloon. This cold balloon, the molecules aren't hitting the walls very often, so there's not much pressure. Whereas in this hot balloon, the molecules are hitting the walls quite often, so there is high pressure. So what we see is that as temperature decreases, pressure also decreases. And as temperature increases, pressure also increases. So this is a direct relationship. You probably remember in math that anytime one variable increases and so does the other variable, and I'm talking about an x and y axis, that is called directly proportional, as opposed to indirectly proportional, which would mean they do the opposite. So if we graph pressure versus temperature, we see a direct relationship, which ends up being a straight line. And the way that's going to look in an equation, whenever something is directly related, we're going to divide one by the other. So this is actually a good strategy for taking the SAT. If you're ever given an equation that you don't really know much about, you can tell the relationship of the variables based on where they are in the equation. So the fact that, let's say that P and T were on either side of the equal sign, and to get them on the same side of the equation, you have to divide one by the other. That means they're directly related. Whereas if P and T were on the same side of the equal sign, that means they're indirectly related. All right, so that's your first relationship. The second relationship is about volume and pressure. So for this illustration, since volume is different in these two examples, we're going to draw a small balloon, and then we're going to draw a big balloon. So in this first balloon, volume is small, and then this big balloon, volume is large. Now keep in mind, since we're only talking about volume and pressure, that means that temperature is constant. All right, in this small balloon, we're going to be tracking our little molecule of gas. And if we were to track it for about 5 seconds, it's moving at a normal speed. It doesn't take very long for it to hit a wall. Because the space is so confined, it's so small, it doesn't move very far before, oh, it hits a wall, bounces off of it, and then goes to another spot and hits a wall again. Whereas in this balloon, there's more space for the molecule to get around. So if we were to track it for the same amount of time, it's not covering as much ground. It's not hitting the walls as often. So once again, if pressure is measured by how many times those molecules are hitting the walls of their container, how much force they're exerting on the walls of their container, we would say that in this balloon, pressure is high. And in the big balloon, pressure is low. So this is actually an inverse relationship. As V increases, P decreases. And as V decreases, P increases. They are indirectly proportional. So if you were to graph pressure versus volume, you would see an inverse graph. So a line steadily decreasing in a straight line. And in an equation, since it's indirectly proportional, P and V are going to be side by side. They're going to be on the same side of the equation. All right, now we're going to look at our next relationship, which is between moles and pressure. Now for moles, we're talking about the amount of gas, and the variable we'll be using to represent moles is lowercase n. And we're going to be talking about pressure. So in this scenario, volume and temperature are both constant. So since volume and temperature are constant, you're going to have two balloons that are the same size, same volume. And in one balloon, we're just going to draw one dot. And in the other balloon, we're going to draw several dots to represent that there's more gas, there's more moles of gas in this second balloon. So if we were to measure the path of this gas molecule for about 5 seconds, that's how far it got. But in this second balloon, you're measuring the path of all of these gas molecules. So since there's more gas more gases are hitting the walls of the container, you can tell that there's more pressure in this second balloon. So you can say N is small in the first balloon. There's not a lot, the amount of gas is not great. So pressure is small. But in this second balloon, N, or the amount of gas, is large. So pressure is large. So as N decreases, pressure decreases, and as N increases, pressure increases. Once again, we see a direct relationship. So if you were to graph pressure versus moles, you're going to see a direct line, straight line going up. And if we were to put this into an equation, P over N. All right. Well, with pressure, we're going to be measuring pressure using a lot of different units. And you see those units listed below. We're going to be measuring it in atmospheres, kilopascals, millimeters of mercury, and torr. And that is how they are all equal to each other. One atmosphere is equal to 101.3 kilopascals, which is equal to 760 millimeters of mercury, which is the same thing as torr. And you need to be able to convert between those units, which means we will be using dimensional analysis. So let's look at some examples. In this example, it says convert 149.7 kilopascals to atmospheres. So let's start with what we know. We want to get rid of kilopascals, so we move it to the bottom. We put atmospheres on top. 1 atmosphere is equal to 101.3 kPa. So what I'm doing is dividing. 149.7 times 1 divided by 101.3. All right, and that's my answer. And since my original number had 4 significant figures, I'm going to keep my answer to 4 significant figures. So that's 1.478 atmospheres. All right, number 2. Now I'm converting 220 kilopascals to millimeters of mercury. So I start with what I know. I move kilopascals to the bottom. Millimeters of mercury goes on top. So how are those related? 760 millimeters of mercury is equal to 101.3 kPa. So now I'm multiplying and I'm dividing. So 220 times 760 divided by 101.3. And my original number only had 2 significant figures, so I'm going to round my answer to 2 significant figures. So even though I get 1,650, I'm going to keep my first 2 digits and round that 6 up to a 7. So I get 1,700 millimeters of mercury if we follow our sig fig rules. All right, now we're moving on to Dalton's law of partial pressure. And this is kind of an easy concept. Basically, and I'm going to use a balloon as an example because that's what we've been using. If you had a balloon that had a bunch of different gases in it, like helium, hydrogen, oxygen, nitrogen, and you wanted to know what is the total pressure in this balloon, all you would have to do is add up the individual pressures of each of these gases to get your total. So it's as easy as addition. Now, there is one application of this law that can be a little confusing, and that's why I have this little drawing here. I know it's not great, but I'll try to explain what all of this is. So in this test tube, this is supposed to be a test tube, believe it or not. In this test tube, imagine you have hydrochloric acid and zinc. Now, when zinc and hydrochloric acid react, You probably recognize this as a single replacement reaction, so you're left with zinc chloride and hydrogen gas. So the hydrogen gas is going to bubble up out of the solution, and what I have up on the top of the test tube is a cork, and coming out of the cork is a rubber tube. Now this tube is collecting the gas, it's collecting the hydrogen gas, and it's coming over here. This is a beaker of water. And what I have in the water, this is supposed to be a graduated cylinder. So imagine that this graduated cylinder had been completely submerged and it was turned upside down, still in the water, so that right now it's completely full of water. All right, and it's not until you remove the graduated cylinder that the water comes out. So right now, imagine it's completely full of water. And it's not until the hydrogen gas comes through this tube to the graduated cylinder that these bubbles start to displace the water in the graduated cylinder. So you start to see, starting at the top, you start to see gas forming, and you see the column of water going down. All right, so this is a common way that we collect gases in chemistry. And the thing that you have to remember is if the purpose of this lab was to figure out the pressure exerted by hydrogen, the way we have to figure that out is we need to know what the atmospheric pressure is in the room. Now, all you have to do for that is to just go online and look at the barometric pressure for wherever you are at that point. So that's normally when we do this lab, I just look up on weather.com, what is the barometric pressure for Roebuck? So that would be your atmospheric pressure. That would be the total pressure. But the thing you have to remember is that the atmospheric pressure and the partial pressure of that hydrogen filling the graduated cylinder are not equal. They're not equal because there's something else exerting pressure in this graduated cylinder, and that is water vapor. So the water is also exerting pressure. So you have to keep in mind that the partial pressure of the water and the partial pressure of the hydrogen added together equal the total barometric pressure. So if you wanted to figure out the partial pressure of hydrogen, all you have to do is subtract the partial pressure of water from the total pressure. So that's what this next problem is about. Let's look at it. It says helium is collected over water at 25 degrees Celsius and 1 atmosphere of total pressure. At 25 degrees Celsius, the vapor pressure of water is 23.8 torr. Calculate the partial pressure of helium. So you've got to keep in mind our equation up here. P total, or P, I'm going to put ATM, atmospheric pressure, that's the same thing as P total, is equal to the partial pressure of the water vapor plus the partial pressure of helium. Now, they told us in the problem that the partial pressure of water is 23.8 torr. And they told us that the atmospheric pressure, or the total pressure, is 1 atmosphere. So we're trying to figure out, sorry, that should be a plus sign. We're trying to figure out what the partial pressure of helium is. Now, before you go to subtract, you need to realize that we have 2 different units here. We have atmospheres and we have torrs. So we need to convert one to the other. And if you don't remember what that conversion is, you can look back to our original sheet, or the last sheet we looked at. 760 torr is equal to 1 atmosphere. So I can simply, rather than writing 1 atmosphere, I can just change that to 760 torr equals 23.8 torr, which is added to the partial pressure of helium. So I need to subtract those 2 numbers. and I get 736.2, and that's it. All right, now we're going to end today by talking about the different gas laws, and these are all based on the relationships that we've already covered. The first one is called the ideal gas law, and the equation for that is PV equals nRT. A lot of times people refer to this equation as PivNert. So if you hear me say PivNert, that's what I'm referring to. Now, just to go over what all the different variables in this equation mean, P stands for pressure. So that's the pressure exerted by the gas on the walls of the container. It needs to be in atmospheres. That's very important. V stands for volume. So the volume of the container, that needs to be in liters. N stands for moles, and obviously that needs to be in moles. So if the amount is ever given to you in grams, then you need to divide by the molar mass. So if amount is given in grams, divide by the molar mass. So then you have it in moles. Now, R is your constant. You probably are familiar with constants and different math equations you've used. It's just a number that's always the same that makes the equation work. But because your constant is in liter atmosphere over mole Kelvin, that's why all your other units have to be specific. So pressure can't be in torr, it has to be in atmospheres. Volume can't be in milliliters, it has to be in liters. Moles can't be in grams. So all of that is based on this constant. And then lastly, T stands for temperature, and that needs to be in Kelvin. You might remember the conversion for Celsius to Kelvin. It's pretty simple. You just add 273. And you get Kelvin. All right, so that is the ideal gas law. Now we're going to move on to our other laws. So Boyle's law up at the top. Boyle's law is the relationship between pressure and volume. And this is if you're ever comparing initial conditions to final conditions. So an initial pressure and an initial volume to a final pressure and a final volume. Now, the way you can remember the relationship, or that Boyle's law has to do with pressure and volume, you can think of this little acronym. You boil peas and veggies. So boil, P, and V. Boil peas and veggies. And I'm going to give you a few practical examples of this. As you might remember, hopefully from a few sheets ago, pressure and volume are indirectly proportional, meaning as one increases, the other decreases. So the first example I'm going to give you is that of a water bottle. If you were to take a sealed water bottle and take it to different elevations, keep in mind that when you're at high elevation, there's less pressure because there's less air, right? And so if you were to take that water bottle from a high elevation to a low elevation where the pressure is higher, since volume and pressure are directly or indirectly proportional, as pressure goes from low to high, you're going to see the volume of that water bottle decrease. So if you started like on the top of a really, really, really high mountain with your sealed water bottle, you go to the bottom without releasing any pressure, you'll see it shrink. So that's your first example. The second example, I'm not going to go into a lot of detail here because this is actually something you're going to research next week. But a sickness known as the bends, this is scuba diver sickness. This is also a result of this relationship between volume and pressure. All right, moving on to Charles's law. This is the relationship between volume and temperature. And the way you can remember this is Charles watches TV. So for this one, keep in mind that volume and temperature are directly proportional. As temperature increases, volume also increases. So an example I'm going to give you here is what happens to your tires in early spring. So if you ever go out to your car on an early spring morning where it's kind of cool, it's really cold outside, and you looked at your tires, you might notice that they're a little low. It's not necessarily because they've lost air and that you need to refill them. It might just be that the temperature got cool, so did the gas inside your tire, so there's less pressure. So the trouble is, if you were to quickly refill your tires and then that afternoon when it heats up and you're driving down the highway, now there's more air in your tire than there should be, so that could cause your tires to pop. So that's just an illustration of the relationship between temperature and volume. The other one, this is another one I'm just going to touch on. You are going to do research next week, is how do hot air balloons rise? So the hint is that it has something to do with the relationship between volume and temperature. Now you might be thinking, oh, that's easy, but it's actually a little bit more involved. You're going to have to look into air density. That's my other hint. All right, moving on to Gay-Lussac's law. This is the relationship between pressure and temperature. So remember that pressure and temperature are also directly related. I don't have a fun little acronym for you. Just remember it's the third one, process of elimination. But my example is if you were to ever throw an aerosol can into a fire, what would happen? So an aerosol can is like spray paint or hairspray. It's a can that's already under pressure. You throw it into a bonfire, the increase in temperature is going to cause an increase in pressure, so the can will explode. And now for our last law, it's the combination of all of these, the combined gas law. So if you look at all the equations you've seen so far, pressure and volume are indirectly related, so they're always side by side. Temperature and volume, temperature and pressure, those are direct relationships. So temperature is always on the bottom. So when you combine all those together, pressure and temperature are side by side. Sorry, pressure and volume are side by side. Temperature is always on the bottom. So that's the combined gas law. All right, lastly, what does STP mean? STP means standard temperature and pressure. So the science community came up with a set of conditions where it's best to study gases, and those conditions are 1 atmosphere of pressure and 0 degrees Celsius, which is freezing. Now keep in mind, whenever you use these laws, your temperature should always be in Kelvin. You might want to write that down. For all the laws, temperature should always be in Kelvin. So whenever you see STP, it's going to be 273 Kelvin. For the other variables like pressure and volume, for these gas laws on this sheet, they just need to be the same unit. So pressure should always, P1 and P2 should always be the same unit. V1 and V2 should always be the same unit. But temperature, no matter what, needs to be in Kelvin. But do remember that for ideal gas law, you do have to use specific units for that one. On part 3 of these notes, I'm going to work some problems with you and show you how each of these laws applies.